our trained data here. So today I wanted to go over eigenvectors and come up with an interesting way to show you guys an interesting way to find the first eigenvector of a matrix. So typically eigenvectors, there's the equation AV equals lambda V, where A is your matrix and V is your vector. And lambda is your eigenvalue. So the eigenvector solves the equation AV equals lambda V. And that equation, when you multiply each side by A and you subtract lambda V from each side, you end up with what's called the characteristic equation, determinant of A squared minus lambda I is equal to 0. And the solutions for that equation are the eigenvalues. And then you plug the eigenvalues back into AV equals lambda V to get the eigenvectors that correspond to the eigenvalues. That's like the way the software would do it. But here's an interesting, different way that I think reveals something interesting about eigenvectors. And so I'll show you in the code. So what I'm doing is I'm taking Mtcars. I'm selecting 6 of the columns: weight, miles per gallon, displacement, horsepower, cylinder, and transmission. I'm turning it into a matrix. I'm multiplying the matrix by its transpose to get the covariance matrix. I'm saving that as a data frame called Mtcars covariance. And then I'm also creating a vector that's of the same size, which I'm just calling vector 1. And here what I'm doing is I'm doing the percent sign with the star with the percent sign to do the matrix multiplication, Mtcars covariance matrix multiplied by the vector that I created. I'm calling that vector 2. And then with vector 2, I'm dividing vector 2 by the norm of vector 2, which is its length in Euclidean space. And after that, I end up with vector 2. I plug vector 2 back into Mtcars covariance. So I multiply my original covariance matrix, my square matrix, by my new vector, vector 2, to get vector 3. And then I take my original matrix and I multiply it by vector 3. And so here I created a for loop. I'll iterate that 10,000 times, which will take just a minute because for loops in R are not super fast. And then after that's done, I'm going to find the eigenvectors of my covariance matrix. I'm going to compare it to my first vector, and then I'm going to compare it to my final vector, 10,001. And you will see that here I get my eigenvectors from my eigendecomposition using the eigenfunction, 0.006 at the top, negative 0.001. These are just the eigenvectors. And so in vector 2, I have 0.004. And in the bottom, I have negative 0.001. But my 10,000th iteration, you will see, is actually closer to the first eigenvector than the second vector. So this works in the limit. As you iterate it over and over again, the vectors drift towards a particular direction. So you can think about the eigenvectors as being the representation of a certain process. And this works for any vector that you plug in for your matrix multiplication, as long as it isn't zeros all the way through. I just chose 1, 2, 3, 4, 5, 600. And then I end up with a way of coming up with the eigenvectors. Maybe this isn't like necessarily practical in the computation, except that when you solve the characteristic equation, you have to divide by the determinant. And if the determinant is a number that is like almost 0 by 100 digits, then you'd be dividing by an extremely huge number, which could blow up the computation in 64-bit processing, whatever. So, maybe it would have some kind of application, but maybe not. Maybe it just reveals something kind of particularly interesting about how eigenvectors can be understood as a representation of a process, and how the matrix times a vector that creates a vector will eventually when iterating itself, drift towards the direction of the eigenvector.